So far in all of the thermal processes that we've seen, especially ones that are kind of more intuitive, like in the everyday world, all of them have a direction that things go over time. So for instance, the two block example where they were connected by a thermal conductor, over time, the cold block gets warmer, the hot block gets cooler, they reach a final temperature which is in between the two temperatures. The equilibrium was between them. The cold block didn't get colder and the hot block didn't get hotter, although why not? I mean, our intuition tells us that that can't happen, but there's no law yet that says that that can't happen. Similarly, if you had, let's say, green particles on one side of a box and then you removed the divider between two halves of the box, the green particles would then fill the whole space, but it would be very difficult for those green particles to recollect on the same side of the box. The system evolves in time to have the particles evenly distributed. And similarly, when you have an ice cube in a warm room, over time, the ice cube melts and becomes liquid if the room is warm enough, and you're able to change the state of that matter, and it goes in a particular direction because the heat has to travel in a certain direction. Heat goes from hot things into cold things. And yet we haven't actually explained that. We've only just been relying on your intuition that that's going to be the case. So the question is, why? Why is it that when you have two objects, a cold one and a hot one, and they're connected, that the cold one gets warmer and the warm one gets colder instead of the cold one getting colder? I mean, why can't the hot one just draw out energy from the cold one? So far we've had two laws of thermodynamics, and let's see if either one of them can help us with this. The first law, the zeroth law, it just says that the cold block, if the cold block temperature and the hot block temperature are the same, then the thing in the middle is also the same temperature. It has nothing to do with how it gets to whatever temperature it's at. It just says if they're in equilibrium with each other, then they all have the same temperature. And that doesn't really explain this process at all. The first law is a conservation of energy law. So it may be able to explain this because it does actually talk about heat transfer, that delta Q, but it actually doesn't give us any direction as to how these things should change. So there's no reason in the first law why the hot block can't just get hotter. It doesn't tell us that delta U for the hot block must decrease. It also doesn't tell us that the delta U for the cold block must increase. There's nothing in the first law that helps us here. So that's a little strange. And that means that we're missing something. This cannot happen. So that means we must need another law. And just spoiler alert, there will be another law, but we're going to build up our intuition about how to think about this law in a logical manner. Okay? And so what are the things that this law needs to talk about? It needs to talk about the direction of processes. It needs to say that heat can only travel from hot things to cold things and not vice versa. So it has to talk about the direction that heat can travel. Okay. And in order to think about this, we have to think about what does it mean for these processes to occur spontaneously in a certain direction. Why can't heat flow from a cold object to a hot one? And actually, you know what? It can't. There's nothing in a conservation of energy stopping it. But it's just a very low probability that that would happen. Very, very low likelihood. So let's do another example. Let's say you have particles in a box, and now I'm showing you the actual individual particles. You have many particles in the box. There are two distributions of these particles that I'm showing you, and I'm saying they're both equilibrium states. One distribution has the particles evenly distributed. I'm not showing you their velocities, but I'm telling you that the velocities are also distributed evenly in the sense that there are just as many going right as left, just as many going up as down. Now let's look at the other possible distribution. This one has all the particles on the left side of the box, and let's say they're all moving in the same direction, towards the right side of the box. So this state seems very unlikely, right? It has a low probability. The one where the particles is kind of seemingly more random, that's a higher probability. And so these two different states, although, you know, for this any one state, if I took a snapshot of that state, they all have actually the same probability. But for the types of states that look like the one on the left versus the types of states that look like the one on the right, it's just going to be more possible states that are kind of evenly distributed than there are for all the molecules to be in one half of the box. In addition, there's another way to think about this, which is that the box on the left-hand side just is going to have less ability to do work than the box on the right-hand side. What does that mean? I mean, well, first of all, the center of mass of the particles in the box on the left-hand side is in the middle, whereas the center of mass for the right-hand side is not. And it has all this room to expand to the right-hand side. And if it did, the center of mass would move. And that would mean that it could do some work. It would have some overall momentum. In fact, the box might slide off the table if all of these particles all moved to the right at the same time, right? Because they would be carrying momentum with them and they might slide the box off the table. Whereas we know a box of molecules is not sliding off of a table spontaneously, so the molecules must have their center of mass in the middle, and that center of mass must stay put in the middle. It must not move over time. And so this kind of center of mass or momentum argument, it also says that the box on the left is more likely, and it's actually what's actually happening with these molecules, whereas the box on the right, lower probability of happening and more capacity to do active work, more ability to move, create a force to move the box off the table, but that's just not happening. So in order to kind of, get these ideas together, we need a new thing to measure, what we call a metric. And we're going to invent a new metric, and we're going to call it entropy. Now, obviously, we're not the first ones to invent this, and I'm trying to actually teach this to you, but the idea is that this idea of entropy is actually a measurement of the probability of the states. And so, in particular, the states that look like the one on the left, which are many, there are just many more states that look like the one on the left than there are than the ones that look like the one on the right, where the particles are evenly distributed. And this entropy is going to measure how many different states look like that one on the left versus the one on the right. And so we're going to use this entropy to measure this probability. We're going to use S, capital S, to represent entropy. And in the case of these two things, we can say that the entropy of the box on the left, of the particles in the distribution, or distribution similar to the one displayed on the left, those have higher entropy. Whereas for the box on the particles on the right, those have lower entropy. And so now that we have a way to quantify this probability, like the probability of being in a particular type of state, now we can use that to say how systems will evolve over time. And in particular, we are going to say that we're going to take that probability and we're going to say that it's going to have to evolve towards being the higher probability state because it's just more likely. So if we did have molecules that were all on one side of the box, and then they would actually have to evolve to being like the molecules on the left-hand side. They'd have to go towards that with time. And this means they have to go from a lower entropy state to a higher entropy state. That means that the change in entropy, in this case, is greater than 0. The second law of thermodynamics actually states that the change in entropy for a system can either be greater than 0 or equal to 0. But you can never go to a lower probability state from a higher probability state. You can go between two states that have equal probability, but you can't go to another state that is like losing energy, right? Losing entropy. And so the arrow of time must point so that entropy increases. And I know that you've probably heard in other classes or in other conversations that entropy is a measure of the order of a system, but that is just simply not true. Because you, especially in biology, can have many systems that are well ordered, but that are actually driven by entropic processes. In particular, the thing that I study, which is microtubules, the polymerization of a microtubule is increasing the order of the tubulin molecules, but it actually is being driven by the entropy of the water molecules around it. And so, in fact, polymerization, which drives order, it's a process that causes higher order, is actually being driven by increasing entropy of the system. And so I don't like this concept of order. This is not something we're going to talk about. We are going to talk about probability. And you'll have to be able to think about, well, is this system going to have higher probability or lower probability based on how it looks? And that's how we're going to think about it.